So, yeah, I hope everyone can hear me well, and I hope you're still awake enough after this long sessions now. So I hope you're ready to switch a little bit topics, because I'm just using Pichia pasturage for protein production, and I have some data where I used our new multi-parameter sensors, where we can now measure the dissolved oxygen in shake flask with a really simple method. And so just that you know where I'm coming from. So I'm part of the chemosensor development team. So we are actually only 3 people. We have a dye chemist, a polymer chemist, and I'm the biochemist. So, and we try to get new sensing system in these pill forms that we can just easily drop into the shake flask and then measure with a sensor from the outside. And as I'm the biochemist of the group, I'm just responsible for everything involved around enzymes. So when we know we need an enzyme for whatever we want to measure, I need to find out what is a suitable enzyme, then what are needed modifications that I need to introduce for purification, for immobilization. Then I need to find out a suitable host, which for, as a lot spoiler, is obviously Pichia for the first target. And then I find out the first method for purification, and I test if whatever I modified is still functional, and is everything sufficiently stable, or is my protein degraded quickly. And I'm currently at the stage where the first target enzyme, it's a glucose oxidase, because I try to produce glucose sensors. And I'm mostly at the stage of protein optimization, production optimization. And because when we started doing this, sorry, it's a little bit slow. We started at the beginning of 2022, and everything was severely delayed. So our lab wasn't ready. We waited for a lot of equipment. So, but we needed, as a small company, urgently needed first results. So I started working with our in-shake flask, because it didn't have bioreactor at that time. That only was delivered at the end of spring last year. So I started with just measuring the biomass with our cell growth quantifier from the bottom, and I was able to use an automated feeding system, our list, that we can add to the top. So at least I didn't have to do all the manual handling. Then I also switched to the bioreactor, and in the summer of last year I was able to test and work with the first prototypes of our new sensors, and now we can measure still the biomass from the bottom. I still use this liquid feeding system on the top, and I can also use now data for the dissolved oxygen that I can measure live by just dropping in this little pill. And also we can measure fluorescence with this, because we've also integrated a spectrometer here, a little one, that I don't have used so far, because here I'm not working with fluorescent proteins. Before I go to the real science part, I just quickly want to show what this pill is actually. So the pill has roughly a volume of 1 milliliter, and we just throw it into the shake flask. And we wanted to have a really simple system to use. And currently we have the DO sensing established. The chemists are feverishly now working also on pH sensing, and I started now to also try to get the glucose sensing running there. And the pill is designed to have a nice stable movement while shaking, what I also want to quickly show you. I hope that will start. Yeah. And here you can see how the pill is actually flying around with the liquid like a little boat. This works as long as the liquid is shaking in phase. So that also means, no, it's not working with buffalo flask, I'm sorry. Here you can see with the little red light, that's when we do the excitation. So, and then where we generate the readout in the software. Yeah, and by using this system, I was able to optimize my production of glucose oxidase quite significantly in the shake flask, which I would shortly show you here. So when I started, as I said, I only had the CGQ and biomass, and we quickly needed enzyme to start working and to getting a feeling for all the system. So I did a lot of improvement steps just with this system. and I managed to get at least a nice 10-fold increase with a lot of variations and tests, and that took me 26 experiment runs, and each run contained several replicates, so this was translated to 200 list cartridges that I used. By this, I became our own best customer for this system. And so this also means this were more than 200 single culture runs. And this whole work took me roughly 3/4 of a year. And when I was finally able to also use the MPS sensor, the very first run that I actually did with this was so nice that I was convinced for every other clones I had in pipeline that I wanted to test, I would be able to reduce all this effort to a few experiment runs with less than 20 cartridges in 1 to 2 weeks, and this is what I wanted to show you now. And at the end, I also switched actually a batch growth in my shake flask to direct immediate fed batch growth, and by switching this and reducing further oxygen stress, I was able to further increase my yields to, that's nearly half what I reached in the bioreactor now. So yeah, when I started doing this, I first looked, of course, how is the process done in bioreactors, and I think I don't have to explain to you here in detail how this is done. So I looked at all the data that we collect, the different phases that we go through, and also that's important too. I knew we need a close DO monitoring because obviously the cells need the O2 to convert also the methanol and do protein production. And I knew pH maintenance is important. But when we go now to the shake flask, of course, I could only start with a batch phase. I could only measure the biomass, and at least I could measure the biomass online without interrupting the system. I skipped the batch phase, the fed batch phase, and directly then went to a methanol induction phase. And just with this system, I played around quite a bit, and I improved stepwise, so tested out different feeding strategies. I looked for an optimal time point for induction for this specific clone. I looked for, I should point there, the amount of methanol that I actually need, because I didn't want to overfeed, but I want to give enough methanol. And I would also test it or playing around with buffering the feed and different filling volumes and what you could think of. And I also checked for the optimal adaptation time that this clone actually needs to switch the metabolism and to protein induction with methanol. I don't want to go into too much detail here, just want to quickly show you the data I obtained for the adaptation time, because that was rather nice when I then went also to the bioreactor. So for this specific clone, I found out it doesn't actually matter to wait longer, so an adaptation time of 7 hours was really sufficient here. And so whenever I did these production runs, I just went for 7 hours of adaptation time before I then went to a constant methanol feed in my shake flask. And when I then did the first few runs in the bioreactor, I was actually surprised to see when I did the adaptation with 1% methanol in the bioreactor, in all runs, it took nearly exactly 7 hours until my DO signal then recovered and the cells did the shift for this clone. So I found that rather nice, but all these tests were done rather blindly in shake flasks, right? So when I was finally able to test the new sensor and the DO sensor pills, I just used my optimized production system that I now had, because I knew these are the adaptation time that worked, the amount of methanol that was fed, and I just added the DO sensor pill to the system and just wanted to see what actually happens. And I really also felt like a little child on Christmas when I came to the lab and had all these data in 1 inch from shake flask. So we could nicely see that the batch phase looks like it would be expected here, so DO goes down to 0 for quite some time. And I optimized the time point for induction blindly to just start when the DO was actually recovered. So I found that really nice. And then you can see that actually the constant feed started a little bit too early before the DO signal was recovered. But after the first few shots, every time my DO signal was recovered, which hints that I didn't have any accumulation of methanol. My cells could actually consume that very well and produce a nice amount of enzyme. The next thing I was able to do is our software engineers nicely implemented a PID controller for me. Oh, actually, I also forgot that I really liked this little bump here, because I could also see this shift in the bioreactor where the metabolic shift happens. Yeah, I forgot that. Because I'm so excited about the DO-based feeding that I was then doing. So our software engineers implemented a PID controller, so I could use my DO signal now to control the feed. So I could always only give a shot of methanol whenever my cells were ready to consume more methanol. And I would be sure, and I didn't need to find out again how much methanol I would need to feed. And when I did that the first time, I was also like, wow, that looks nearly exactly like the one run that you've seen before. So when I did all this optimization, and when I used an automated control here, this ended up with nearly the same results. This time the feed only started when the DO signal was fully recovered. And you can also see that, or I was also surprised to see that nearly the same amount of methanol were fed in comparison to what I optimized before. And also the yields that I obtained were nearly the same. So here you can see the yields that I obtained with 40 or 20% methanol in my feed, with the biomass-based feeding that I did before, and this is now the DO-controlled feeding. So by having all this data, I was becoming a little bit bold, and I was like, okay, I want to do the next step. So I wanted to introduce also a fed batch phase to increase my biomass like we would do it in bioreactors. So I started with the batch phase growth, then switched to a fed batch phase where I just also included glycerol, and then I switched out the cartridge to methanol and then did again a DO-based feeding. And as soon as I did that, I got nothing. So I lost all my protein, and I still don't really know why. So as soon as I add only the tiniest amount of glycerol in a fed batch phase, and also if I increase the amount of glycerol in my batch phase, I lose all my protein. And I was sure that might just be an effect of the complete missing pH control. So, so here you can see how much the pH is actually decreasing when I increase the glycerol in the feeds. And when I then increase the buffer capacity and playing around more with buffers, that actually didn't really help. So I got just a little bit of protein back, but nothing worth using. So I still don't really know what happened here, so if anyone wants to discuss that later with me, I'm really happy. But I didn't have time to look for this because I just need protein. So I tried out what happens if I skip the batch phase, try to avoid so much oxygen stress on my cells, directly go to a fed batch phase, and here I use actually an exponential feeding phase, so the glycerol is added more and more when the culture starts to grow, and then I switched to a DO-based feeding, and by this I obtained really nice amounts of protein, and I really liked also the DO data that you see. So this is just the fed batch phase in the beginning. So the very first shot was given in the beginning, just 100 microliters, so just a really small amount, and then you can see the cells nicely react to each little shot, and the DO recovered until the last third of the feed, and then I had a small phase of oxygen limitation until the cells recovered, but of course much less than I have with a batch phase growth. And just to sum the results of the first construct up, so I first did a stepwise increase just with the biomass signal and the automated feeding, and by this I used 200 single experiment culture runs, and that took me all over the time, just when I look into calendar, nearly 1 year. And the bioreactor still gives me nice amounts, and here I so far only did 4 single experiments, 4 improvement in 4 weeks, and I've of course get in 2 liters a decent amount of enzyme to work with. By using now the MPS sensor and the DO sensing pill, I was able to replicate all the effort I did in nearly 1 year in just 1 week. And then by switching from a batch phase to a fat batch growth, I was able to further increase my protein yields. So, and at this point, of course, not everyone gave me exactly these amounts of enzymes, so I started to feel the most variable I have now is actually the happiness of my starter cultures. So I started looking into this. I had one culture that was maintained for a longer time in the lab, so was in the fridge in between and used to always start new cultures. And then I started a new culture fresh from my cryo stock that I let grow for 2 days. So this one was inoculated from a culture in the fridge for 2 days. This one was started fresh from a cryo culture, and this one then started from this culture after 1 day of growth. So this culture was then actually in the exponential growth phase, and all cultures were started with exactly the same cell densities. And you can see that the freshest, and I like to say the happiest culture here, was able to have the smallest oxygen limited phase. So these cells reacted the fastest to the glycerol, so seems to be like able to consume that, the glycerol the fastest. And also when I then switched to the methanol induction, I could see so the signal was triggered only, so the first adaptation shot was triggered only when the DO signal reached a certain value, so basically recovered. And then I implemented a starvation phase of 4 hours to be sure that all the glycerol was consumed before the shot was then given. And then I didn't set any adaptation time because I said then to the PID controller, start with feed as soon as the dissolved oxygen recovered. And you can see that only the freshest culture actually had an adaptation time of 7 hours, and the others took longer, especially the oldest culture took much more longer until the DO signal recovered. And what I also found very interesting is in the overall feed that was then controlled later, all the settings were all the same, was different through all the cultures, and actually this and this was the same, and there we had much more feed. And actually the protein yield that I obtained were nearly similar for all these cultures. So I got just a tiny bit more on the freshest culture, but nothing to call significant. So I was rather happy that it seems that now my PID controller levels out a lot of the effects that we see depending on the happiness of the cultures. But still, that's something to consider. So in this very last thing I tested is I transferred now the system to different constructs that I had. So, and also here you can see that different construct, different clones also behaved differently to also the glycerol feeding as well as to the methanol feed later. So there we definitely have different adaptation times, different rates of methanol consumption as was expected, but I could nicely see this now also in my data. And yeah, by this I will shortly sum up. So I confirmed that I could transfer that to other clones, and actually the very first thing I transferred to when I went to the new constructs were just with the data that I obtained with the biomass-based feeding. So just my blindly optimized feeding strategy that I had, I transferred to 2 different constructs. It's the same enzyme, just different modifications. And here I see that I saw that actually just using that settings wouldn't help. So I would have to do all this work really again for different clones, different constructs. And but luckily now I had the MPS sensor and the DO sensing pill. So I was able now to repeat the experiment. So I just did 2 experiment runs with 4 replicates, and where I used then the glycerol fat batch phase and then the DO controlled feeding with no settings between. So I just let everything be controlled by the DO signal, and that significantly increased my protein yields. And at least one of the constructs I have also now transferred to the bioreactor, and there I see that they also perform less compared to this one. So I assume that the levels of protein expression here are actually pretty decent. So by this, I would like to thank especially my colleagues working furiously on all the sensing systems. So Felix, who is the mastermind behind all the dyes, and Julian, who is behind all the polymers and trying to get the enzymes and the dye together on the pill without hating each other too much. And also I would like to thank Jim, who recently left our team to go to the dark side of the commercial team, not his own fault. So, and by this, I also like to thank the big kids in the company, which is a great atmosphere, and also all the small kids and the next generation of scientists, and of course, you for all your attention, and I'm happy to answer any questions.
Thank you, Christina. I may have missed it. The work you did was wild type AOX1 plus?
Yeah.
Have you tried the mutton slow?
So I work with the Pichia pink system. Maybe I was too fast in one system to yeah. But I didn't have the capacity or the time to optimize anything of. I have all the different secretion vectors also available from in nitrogen and stuff, but so far I didn't have time, and that always went down on the priority list.
Thank you very much for your presentation. So I have a question about the biomass. So after you grow in the shea flask and induce for around 72 hours with the methanol, how much was the wet cell weight you really got from for your cells?
The wet cell weight?
Yes.
The wet cell weight is usually around 2-something gram. I mostly focus on the dry cell weight, so I know that's always around 0.4 gram in these 25 milliliter that I always use.
Converting it to like grams per liter?
I can't do that in my head.
20 grams per liter?
Not with the jet lag.
1/5? Yeah.
Per dry cell weight times 5.
Okay, yeah. Yeah, the reason I'm asking because we usually got about like 400 grams per liter if we grow in a bioreactor. So I just want to compare if we do this in the shea flask as your method, and how robust this is compared to the bioreactor.
Yeah, so cell weights are definitely different to what we reach in the bioreactor. Yeah.
Yes, and can I ask a second question?
Yes, please.
So I can see you do your methanol feeding strategy as like interval feeding. So do you think that because every time you see the spike, the cells is probably already under the stress of starvation? Do you see like maybe like cell lysis, or do you consider like switching to a more like continuous feeding instead of such an interval feeding?
So I actually tried, that's the best continuous feeding that I could get, because that's just one droplet that is given each time. Oh, yeah. And I can't go more down with the volume.
Small, yeah.
Yeah.
Okay. Thank you.
You're welcome.